So, till last week, whatever the topic that you had is just introduction to wave maximum. We have dealt about progressive waves in transverse wave format. Now, here the question is, what exactly when two waves cross over at a point? If I am discussing about two particles, then I need to say something called a collision. If I am speaking about two disturbances, I am speaking about a superposition. For waves, we will call that interreaction as superposition. For particles, we will call that interreaction as collision. Now you can see you have a string here. You have a string here. This string carries two pulses and they are moving in opposite direction. A is the point where expected superposition takes place. And this is how superposition takes place. They are superposed. And after superposition, the resultant wave takes this form. The resultant wave takes this form. And this we will call as a final superposed wave. And in this case, the amplitude of the resultant wave is more than the individual amplitudes. You can say sum A1 plus A2. Such a superposition is called constructive superposition. Okay. On the other hand, you see you have two pulses traveling in the same string, but in opposite directions. At the point A, suppose if the amplitudes are same, in the process of superposition, you will say the string a flat point. Net amplitude is 0. In all these cases, energy is conserved. Please remember, there is no loss. In fact, the energy may be converted into the form of kinetic energy of these points. And thereafter, say after superposition, the portion as if nothing happened. They move away as if nothing has happened at A. So the pulse that is traveling towards the right is continuing in the same way without any change in its amplitude. Similarly, the one which is passing from right towards the left is passing in the same way without any distortion. Next. And far away and far away. And this we will call as superposition principle. I have shown you two superpositions. One, one, you can see constructive superposition. The other is a destructive superposition. Constructive and destructive. Right. Till here, any doubt? Boys and girls. Right. Now, in general, the superposition is described as a function as superposition y is equal to y1 plus y2. Same thing you have done in electric fields also, E1 bar plus E2 bar. When two or more waves or wave pulses passing through a given point simultaneously, which means at a same time. The resultant amplitude or displacement is given by this equation. Y bar is y1 bar plus y2 bar. This is the superposition principle. See, in a collision, we have a clarity what is happening. Exchange of momentum takes place. What is happening in case of the collision of a pulse? Now I will clearly discuss over here. Now, when a pulse travels in the forward direction through a string, two things might happen. One, maybe the string throughout is not the same. Two, it might encounter a boundary. Boundaries are again two types. One is a rigid boundary, the other is a free boundary. When it meets a rigid boundary like this, what happens? You see this pulse reaching rigid boundary. Remember, the thumb rule is the point P cannot displace. So therefore, the reflected wave is such that all the time the point P is zero displacement. Now you see, the wave would have progressed like this. The reflected wave would have progressed like this so that this end cancel with each other so as to make P zero. So in reality, the shape of the pulse takes like this. Earlier it is like this. Now here it takes a shape like this. Thereafter, what happens? Almost this entire portion becomes a flat. Thereafter, what happens? What appeared here will appear here in the inverted fashion. And thereafter, it continues in that direction. So, what is that you need to note is at a rigid boundary, crust gets reflected as a trough and the trough get reflected as a crust, which means a phase difference of pi will be there between the incident and the reflected wave. This is the point to note. Any doubt in this, please ask me right now. Similarly, reflection at a free boundary. How to imagine a free boundary? You imagine the string here is connected to a light ring, light pole, some mass is there. And this is some rod-like structure, thin rod-like structure, along which the ring can freely move. When the disturbance reached this point, remember, unlike point P here, this point can move. So what happens is that point will move. When the entire pulse reaches this point, what will happen is, the superposition of the forward coming wave and the superposition of reflected wave pulse, both take a constructive superposition. As a result, the ring will go till here. And again, the process gets repeated in the same sense, like this, and it travels in the same sense, which means the reflected and the incident are in the same phase. This is some theory related to reflection of a wave at the free boundary. Actually, we are supposed to do some numericals on this. You take a case like this here. Is this model covered? Right. The amplitude 0.1 mm, 4 centimeter, 2 centimeter per second. And that pulse is 4 centimeter from a point P. No idea about what is P. Now you take first case, P is a rigid boundary. You take the second case, P is a free end. Now we will work on this. This is a T is equal to 0. Lot of things were there. Yeah, yeah, yeah. Right. We will take a new situation. This is what shown at t is equal to 0. Right. Right. Now the question is, at P being rigid boundary, what we will do in that case is that we will construct again a similar wave pulse which is at 4 centimeter, but pulse being inverted. Now this is the situation we have. Now what happens is 2 centimeter per second. Now they will ask every 1 second what is the situation. For example, this is at t is equal to 0 picture. Right. Now what we are going to do? We are going to do at t is equal to 1 second. So what is going to happen? Now t is equal to 1 second. This part will move by 1 centimeter, 2 centimeters, right? And similarly, same thing happens over here. So what we will do is this is the point P. Now you can see here, this is a 2 centimeter here, 2 centimeter here. Next 1 second, what happens? Again, this will move further by This is now at t is equal to 2 seconds. Similarly, the reflected wave, like this. T is equal to 2 seconds. 0, 4 centimeters, 4 centimeters. Now here after every t is equal to 1 second, what happens that we need to check with. Now actually what will happen thereafter at t is equal to 2 seconds, yet t is equal to 3 seconds. What is going to happen? Yet t is equal to 3 seconds. What actually supposed to happen is actually what has to happen is this. But is it possible such a situation? No, such a situation is not possible. That is the reason why the waveform will take a shape like this. A shape like this. You can see next shape is like this. So, which means at this point, the shape of the wave, when this is the point P, the shape of the wave, this is the point, where is point P? 3 is equal to 2 seconds. The peak come over here. This is point P actually, location of point P. Because for every 1 second, it travels 2 centimeters. That is point P. Get the point? Now, previously, this is O. Now, this has moved to this point. This point, this particular line shifted over to here. Shifted over to here, like this. Very clear. Now, what happens? The entire part will get cancelled. See, try to please understand, all these parts will get cancelled. Cancel, cancel, cancel. So what will happen at this point of time? See, this entire part, whatever it is, now gets cancelled. Now, which means if this is a rigid end, what will happen is the point will not move, becomes flat. Becomes flat. So again, at t is equal to 3 seconds, 4 seconds, what happens is actually I think I would think what I have done is I would wrong. This is Ari, if that also moves by 2 seconds, what will happen is this is 4 seconds, no? This is 4 seconds, no? If this moves by 2, this will also move by 2, no? And this is point P. That's the situation. At this point, what will happen is it will become flat. Remember, there is no incident as well as reflected there. What you will see is a flat. Next, what happens is next what happens is you will see the flipping of this, which means you will have like this. That is the situation. Point P. Finally, this is the reflected wave, and therefore it keeps moving leftwards. Now see different stages. Stage 1, stage 2, stage 3, superposed stage, stage 4, and thereafter, you know what to do. Thereafter, what happens? Yeah, it keeps continuing like this. It keeps continuing like this. Disturbance. Like this. And here is your point P. Did you notice it? Superposition zone there? Remember, this is a rigid boundary. What happens if it is a free boundary? Can you please plot that? This is all a rigid boundary. What happens if it is a free boundary? That you plot right now. Now, don't forget, if P is a free boundary, two centimeters, 4 centimeters. Right? It moves like this. It moves rightwards. And this is a free boundary. And this is the instant at t is equal to 0. Now what you will do is, if it is a free boundary, it goes like this. Now what happens? It goes rightwards. Same time, only for our convenience, we are writing the dark line. Remember, black color one, reflected. Practically, it won't exist. Only for our mathematical convenience, we are writing that. Next, this is at t is equal to 1 second. Remember, this is a 2 centimeter and this is a 2 centimeter. Now, next, what happens is, frankly speaking, point P. Point P. Whereas the black line will also come over here, crossover. Now tell me what is going to happen. Actually, at this region, the actual color line will go till here. Now this is t is equal to 2 seconds. There also remember, Your observation 0 second, 1 second, 2 seconds, 3 seconds. Here also 0 second. Actually, there 4 centimeters we took it as 0. That is the reason why we got the difference. Suppose if t is equal to 0 is taken, then obviously it is correct. Same interval you have seen the superposition stage. Only difference is now you see that it is above. You can see 2 times the amplitude of individual things. Then again, what happens at t is equal to 3 seconds? At t is equal to 3 seconds, what will happen is that like this. And at t is equal to 4 seconds, what you have just seen will get repeated, but only thing is the pulse get reversed. I mean, reverse direction. But shape of the pulse or the position of the pulse remain the same. This is superposition. The one which I have discussed is at rigid boundary at point P. The other at a free boundary. Free boundary. Clear? Right. Next. So this is all discussion of reflection of a wave at a boundary. Next. So same thing I have done. And now why don't you try a similar situation for this case? Everyone. I want both the cases. You will have triangle, square. That's all. Everyone start working on this. Now you have exactly 5 minutes to complete both. Now, have you seen the first case? Pulse is moving towards P. Now, if it is a P is a rigid boundary, then what we are telling that this inverted pulse, which is the right side of P, is heading towards a P. Right. Now, this is the situation. Now, thereafter, what happened? Now, you have seen that speed is 2 centimeters per second, and I have interval to the interval that I have taken is 0.25 seconds. 1 second, and next 1.25 second, what will happen? It will move by 0.5 centimeters. See here. If this is P, this moves left by 0.5 centimeters. This will move right by 0.5 centimeters. Now, you can see the actual waveform will be like this at that time. How many got this? Next, flat. Why flat? Are half of this will come like this, upper half will come like this, flat, complete destructive interference. Then what happens? Same thing flips. And thereafter, total inverted wave pulse. And thereafter, it moves like this. Have you followed the same? You got the same drawings? Sure? Pakka? Right. What if it is a free boundary? What if it is a free boundary? You will meet a situation like this. After 1/4 of a second, remember previously this was a dead, flat. Now you see it gets added up. So you will see the string will take a shape like this. But when I am teaching this, please remember, physically you don't see these points. Actually, it may be the shape. That may be, because you will never see a shape like this actually. Actually, this shape is something like this. That we will make our, for our convenience, we will modify the shape like this. Next, when complete overlap takes place, what happens is that instead of A amplitude, you can see it took the shape of 2A amplitude. Don't forget, the full length is 2 centimeters. Here, it took only 1 centimeter. 1 centimeter. Amplitude is 2A. Amplitude is 2A. Full length is 1 centimeter. Again, thereafter, after another 1.75 seconds, same thing. See, what repeated here gets repeated over here. And thereafter, it will take the full shape. Thereafter, as usual, it's a normal. The difference is intervals, 0.25 seconds intervals. Do you got the same shape? Yes or no? Right. Right. So the one is a triangular wave, the other is square wave. That's what I have discussed with you. Next. So I should now discuss stationary waves. What will we see in stationary waves? In stationary waves, we will see that there are two stationary waves, two waves. One is forward moving, the other is backward moving, and they superpose to form a format, a representation called stationary waves. So, what exactly the stationary wave means? See, when two progressive wave trains, one traveling in the forward direction like this, the other traveling in the reverse direction like this, when they if stationary wave format is formed, you will feel as if that there are some loops like structure in that. In fact, there won't be any loop. Actually, the portion of the string within these 2 points vibrate up and down, up and down, up and down like this. Once like this, next like this, next flat, next like this, next like this, and this process repeats. So what you will see is like a loop structure, a loop kind of structure. Okay. Here you see in this loop kind of structure, you will see some regions where displacement might be maximum, some regions where displacement is 0, right? And remember, this entire loop is of length lambda by 2. Why? Because this is your wave, progressive forward moving wave in the absence of other. This is your wave, negative x direction moving in the absence of other. So these points, permanent zero displacements called nodes. And these points with maximum amplitude are called antinodes. Between two nodes, distance is lambda by 2. Between two antinodes, distance is lambda by 2. I should say successive. Between a successive antinode and a node, it is lambda by 4. Remember, actually, if you focus on one such a loop, what happens is, for example, at the instant you have seen the string is in this position between the nodes. Next instant, it takes a shape like this. 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 So, 1, 2, 3, 4, 5. And again, it gets repeated. At after T4, what happens? Again, it comes to this position. 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 So, what you will see is a loop type of arrangement. A loop type of arrangement. Do you got the point? A loop type of arrangement. So, this is what we will see in a loop actually. Remember, for example, at this instant, you see the string like this. The next adjacent portion string will be like this. At this instant, next instant, the string is like this. The adjacent portion string will be like this. At this instant, if the string in this portion is like this, the next string portion is like this, which means If this is moving down, this will move up. And not only that, every particle in this move downwards, every particle in this string will move upwards. So within the loop, all the particles are in the same phase. But this loop and the next adjacent loop, the phase difference is pi. Remember, in a progressive wave, between any 2 points, the phase difference may be anything between 0 to 2 pi. I am repeating again. In a progressive wave, like normal progressive wave, you take any 2 points, these 2 points, these 2 points, these 2 points, they bear a phase difference anything between 0 to 2 pi. Whereas in a stationary wave, either the phase difference between any two particles is 0 or pi. Why? If you are taking within the loop, 0. Within neighboring loops, pi. Got the point? Clear? Right. Now we will try to analyze the stationary wave equation. Stationary wave equation. See, I said you require two waves for this process. One is a wave propagating in the forward direction. The other wave traveling in the reverse direction. Forward direction, reverse direction. When a wave is traveling in the forward direction, you are representing the equation as A sin kx minus omega t. When it is traveling in the reverse direction, means it is in the positive x direction. It is in the negative x direction. Positive x plus negative x. A sin kx minus omega t plus A sin kx plus omega t. You have two equations. Then what happens? Their sum will result something like this. 2a sin kx cos omega t. So omega represents frequency and k represents the amplitude part. In this, you have two components. One, I have just, you know how to do this. A sin A minus B plus A sin A plus B. After working, you will have some equation like this. And this entire term is called amplitude term. And this entire term is called frequency term. Cos omega t is a frequency term. And this is the amplitude term. 2a sin kx is the amplitude term. Right. Next. Now you see what is happening. Just let us try to understand. Let us try to understand. So at x is equal to 0, you know a sin kx minus omega t at t is equal to 0 will take the form a sin kx graph. So I am focusing only a portion of length lambda, 0 to lambda. That's the rule. Similarly, a sin kx plus omega t also graph is like this. Now this plus this. When this is overlapped with this is, don't forget, this is x is equal to 0. This is x is equal to lambda by 2. This is x is equal to lambda. This is x is equal to lambda by 2. Now what is happening? You are overlapping this pulse with this pulse. You will get a huge one. That's what you got here. Huge one. Whose amplitude is 2a. And therefore, this point is called antinode. Similarly, this one overlaps with gives, again, you will get a huge one here, 2a amplitude. So this is the point of maximum displacement. So this is antinode, right? But one thing, please remember, this point, velocity of the particle is minus v times dou y by dou x. Okay, if wave is traveling in the positive direction, v place you will get plus v. The wave is traveling in the negative x direction, in the place of v, you will take minus, right? Now at this point, dy by dx is positive. Dy by dx is positive. And but slope is positive, but it is a negative, minus sign is there. So therefore, at this point, velocity is like this. Now, what about this point? Slope, of course, is positive, but wave is propagating in the negative x direction. So therefore, velocity is positive. Velocity is negative. Area, when two such particles overlap, two such disturbances overlap, resultant velocity is always zero. So therefore, at these points, velocity is always zero. Velocity is always zero. Such points are called nodes. Got the point? The next instant, what happens? After t by 4 seconds, what happens? Exactly after 1/4 of a time period, since the wave is propagating in the forward direction, the wave pulse in that region takes a shape like this. Since the wave is traveling in the negative x direction, it will take a shape like this. Now you need to overlap with this portion with this portion. Remember, these 2 points are common. Hello, previous points. Now at this point, again slope is positive. At this point, slope is positive. Velocity is downwards. At this point, slope is negative. Velocity is in which direction? Hey, downwards. Why? Station wave moving in the negative x direction. Slope negative. Velocity negative. And there is minus sign. 3 minus sign, put 1 minus down. So what is happening? Both are in the same direction. That is the reason why at antinode point, maximum velocity is noticed. Same thing you will find here also. Remember here, negative slope, positive velocity, positive slope. If slope area, if the wave is traveling in the negative x direction, positive slope gives positive velocity. So here it is positive, it is positive. So therefore, here at this point, maximum. These things gets repeated like this. This is how stationary wave works. So therefore, I'll conclude my observation. Important points regarding stationary waves. Within the loop, all the particles are in the same phase of vibration. That's what I commented. I think you got the point. Same phase of vibration. Clear? And similarly, phase difference between two particles in neighboring loop is pi. Next, there are certain points in the medium which are always in permanent state of rest called nodes. I've shown you already that. And a loop is the region between two successive nodes. And the length of one loop is lambda by 2. That also I have shown. See, why? Because I'm just concluding what I taught you till now. Across the nodes, no energy is transferred. That is, energy is not transported from one loop to another loop. Means no form of energy is transferred from left to right or right to left across a node. Why? See, you require power actually for that purpose to happen. Remember, unless or until there is a power, no transfer of energy takes place. But nodes always zero displacement, always zero velocity. How power is delivered? Tell me. So from left loop to right loop or right loop to left loop, no transfer of power takes place. Right. But energy is transferred within the loop. For example, you take a situation here. At this point of time, at this point of time, in this portion, the total energy is in the form of potential energy. Now, what happening over here? The entire potential energy is converted into kinetic energy. So, what was potential energy earlier at this stage is now equal to total kinetic energy at this stage. I'm speaking about half the loop. So now what is form of energy transfer? Node to antinode, antinode to node. Now energy is transferred. Now this is like this. Now energy transfer takes place from node to anti to node within the loop. So what was the total potential energy here is now the total kinetic energy here. The energy is transferred from node to antinode. Next instant, what happened? Again, you will see a stage like this. The entire potential energy here. What was the kinetic energy of this point earlier now is the potential energy at this point. Right? I think you got my point. Right. So these are the observations what I have. But remember, what is the nature of the stationary wave depends on the involving progressive waves. So just now we have seen A sin kx minus omega t, A sin kx plus omega t. For this, the equation is like this. Any equation, omega term represents frequency, k including 2a represents amplitude term. Please remember, please note that. Remember, when x is equal to 0 is a node, usually you will get sin kx. When x is equal to 0 is an antinode, you will get usually cos kx. Remember that. Why should you remember? That's a fact, actually. Next, when you take these two equations, you will get minus 2a cos kx sin omega t. When you take these two equations, you will get 2a cos kx cos omega t. When you take these two equations, you will get 2a sin kx sin omega t. I am telling you again, in case of sin kx term, x is equal to 0 is a node. In case of cos kx term, x is equal to 0 is anti-node term. So I have given you the very fundamentals of stationary waves. Now tell me till this point, do you have any doubt? Next. Identification of wave equation from the shape of the string. You just have seen that at t is equal to 0, the shape is like this. Means the string is like this. Okay, undoubtedly everyone will say sin kx, no issues. Is it sin omega t or cos omega t? How do you know? If you put t is equal to 0, cos term, see, remember, if there is a 2a sin kx sin omega t, undoubtedly this shape refers sin kx, undoubtedly. But at that instant, every particle has maximum displacement. So it should not be sin omega t term. It should be cos omega t term. And then you will get positive. Suppose if the wave is like this, and all the particles are moving down, in that case, very simple, अरे इसके बाद A shape आएगा. So put sin omega t plus pi by 2 for this equation. What is sin omega t plus pi by 2? Sorry, cos omega t plus pi by 2 minus sin omega t. You got the same. So if you know this equation, 2a sin kx cos omega t, you can get anything. No, sir. What about this? Okay. Array from here to this stage, put cos omega t in this equation, cos omega t plus pi. You will get what? Minus cos omega t. Right or not? That's all. You get the same. Right. Also, hereafter, if you see a shape, if you know details about this shape, you can give me details of any other shape. Right? Next. Right. Now we will speak of energy associated in a stationary wave. Don't say since there is no energy transfer, there is no energy associated with a stationary wave. Please remember every point between two nodes is having some slope at some point of time. Means it has some potential energy. Sahi hai nahi? Next, it is in motion. So it will have some kinetic energy. It will definitely have some kinetic energy. Right. Now the question is, suppose I am taking a stationary wave equation of this form. Y is equal to A naught sin kx cos omega t, where A naught is the amplitude of the antinode. This is A naught. Now I'll take one element. This is x is equal to 0 and this is at x. Agreed? Boys and girls. Now, this point is now having two forms of energy. What is the kinetic energy per unit length? Already in a case of a wave, we have already defined that. Half, I think in the very first chapter, very first week, we have defined half mu element velocity dy by dt square. Remember, mu means mass per unit element. Remember, in waves, don't say kinetic energy because point to point it will have different velocities, different slopes. So therefore, you should say kinetic energy per unit length, kinetic energy per total energy per unit length, potential energy per unit length. I think you got the point. So at this kinetic energy per unit length is half mu dy by dt whole square. Don't forget, I have given the equation as y is equal to a naught sin kx cos omega t. So therefore, I am taking dy by dt and it's a square. So therefore, half mu. Yeah, you are doing dy by dt. So cos omega t becomes minus sin omega t. Fortunately, it is a square. So omega square, a naught square, sin square kx, sin square omega t. So for a point, give me location and time. I'll give you kinetic energy. Don't say y2. Come on. Different points have different slopes, by the way. Different amplitudes. So therefore, you wish to ask me this question, just tell me location and time. I can give you kinetic energy per unit length. Similarly, potential energy, standard formula, both the sides. What is potential energy form? Already in the last week class, we have discussed it. Half T dou y by dou x square. So that we have done. Now this time we will get dou y by dou x means k cos kx हो जाता है. So half mu omega square a naught square cos square kx cos square omega t. In progressive wave, remember, in progressive wave, at every element, I'm repeating again, let's listen to me. In progressive wave, at every element, kinetic energy per unit length is the same as potential energy per unit length, but not in stationary wave. You can see that, अरे यार, इसका equation अलग है, इसका equation अलग है, and this one is a different thing. They are two different things. They are two different things. They are two different things. So therefore, not equal to is correct. Now, max I want. Kinetic energy per unit length max. Or max is possible. You take what is the kinetic energy per, yeah, max is possible when sin square omega t is 1. So therefore, that becomes half mu omega square a naught square sin square kx. This is for an element you are giving. And remember, at this stage, string will be flat. When is Ke maximum? When the string is flat. What happens between flat and the topmost stage? The element will have both the forms of energy, both potential and kinetic. The complete upper stage, extreme stage, only potential energy exists. Now, total energy per loop is what I wish to do. Very simple. Can I ask you one question? Within the loop, when the velocities are maximum, what is the total energy of the string within that loop? In which form? Kinetic. So therefore, I know kinetic energy per unit length. So for one loop, I am taking here. Will you allow me this? So that I have done. Here, this part into dx between 0 to L. So mu omega square a naught square by 2 sin square kx dx. So you know, by doing, here I have given sin square kx dx can be written as 1 minus cos 2 kx by 2 dx. And don't forget, you are doing 0 to lambda by 2 actually. That length part is lambda by 2. By doing that, you will get mu omega square A naught square L by 4 if it is in one loop. Right. I am taking L by 2 as lambda by 2 as L. Okay, got the point? By doing, you will get this relation. Any doubts? You ask me. So therefore, you will get this relation. And you should remember this relation, by the way. Total energy per loop is mu omega square A naught square L by 4. L stands for the length of the loop. Next. So till this point, any doubt, please ask me. Don't worry, I'll post you the notes. But I'll post you notes only for this set. Please remember. Do we have a group? Right. What is the name of the group? PK toppers, huh? Right. I'll post it today only. Right. Now, I have introduced the stationary waves. I have discussed about the different forms of equations, and I have discussed about the energy associated with one loop. Now I am discussing about transverse vibrations in a stretched string. Remember, I am taking a loop or a string and I am tightening between two rigid supports. No other option. You need to have nodes here. And I'm plucking that. Depending upon the way how you vibrate it, it may vibrate with a single loop, two loops, three loops, four loops, five loops, n loops, whatever it is. They are called harmonics. If it is vibrating in a single loop, one single loop, it is called fundamental mode. Don't forget, we know the expression for velocity V is this is the notes of your super seniors. So I am reducing, I am just saving time. In fact, you understood what I am doing at this point of time? Saving time. V is T by mu whole to the power of 1 by 2. And okay, it is your choice. Mu can also be written as mass per unit length, can also be written as rho into S. Rho stands for density of the wire. S stands for cross-sectional area. Right. So therefore, what is the expression for frequency here? V by lambda naught. Normal formula. Here lambda naught is 2L because a loop is of length lambda naught by 2. Length of the loop is L. So therefore lambda naught becomes 2L. It will become 1 by 2L root T by mu. And this frequency is called fundamental frequency. Now, depending upon the way, how sometimes you can express velocity term in this form also. Please remember. Velocity term, you can write it in this form. How? Because the tension by cross-sectional area you have. Tension by cross-sectional area is nothing but stress. It can be written as Young's modulus times strain. So therefore, velocity term can also be written as Young's modulus times strain by density under root. Clear? Right. This is the expression for fundamental. Suppose if the loop is vibrating in N with the string, the entire string between the rigid walls is vibrating with N such loops. Boys and girls. Then, okay, fine. The term effect is lambda actually here. Velocity is still the same. So what happens is you have N loops. N times lambda by 2 is L. So where I have lambda, I will now write 2L by N. So the formula becomes N by 2L root T by mu. This is called nth harmonic. Okay. Suppose nth harmonic is hard after n minus 1 times of fundamental. So therefore, this is called nth harmonic or n minus 1th overtone. N minus 1th overtone. Nth harmonic or n minus 1th overtone. Suppose if the string is vibrating with two loops, you will write it as a 2f0 actually. 2 times 1 by 12. Our formula is here. 2 times 1 by 12 root t by mu. 2 times you are writing. So second harmonic. And it is hard after fundamental. So first overtone. Overtone, if I am uttering means how many times later the fundamental. Counting fundamental as 0, you should say overtone. Harmonic aisa nahi hai. It's not like that. Harmonic, you should count n is equal to 1 as fundamental. Right. Now with this, I will define some laws. Laws of transverse vibrations in a stretched string. What is the first law? Ariyar, everything I am now discussing about V is equal to 1 by 2L. V is equal to 1 by 2L root T by mu or 1 by 2L root T by rho s. Everything is discussed on the basis of the same. Now you fix the tension and a given wire. Wire is given. Wire is fixed. Then frequency depends upon the length of the wire chosen, such that F into L is a constant. This we will call as first law. What are these laws? Laws are transverse vibrations in a stretched string. Got the point? So F is inversely proportional to L. You can see that from the formula. Entire thing in the root becomes constant. Once you set tension constant, wire fixed. Entire thing root T by mu is a constant for you. What is the second law? Don't change the wire, but you increase the tension in the wire. And you fix the length also. Then F is proportional to root T, seen from the formula only. Frequency can be written as, F proportional to root T. Next. Now tension is fixed. Okay. Tension is fixed. Two options are there. You change the nature of the wire, copper, gold, silver, aluminum, brass, whatever it is. You change the wire. Rho into S will change. So F is inversely proportional to root mu. But again, in this also, if you are taking same cross-sectional area, wires are same cross-sectional areas, what happens? Wires of same cross-sectional areas, what happens? F inversely proportional to root rho. Suppose wires of same material, different cross-sections. F is inversely proportional to root S. Third law, slight change is there. All these three laws are put together, laws of transverse vibrations in a stretched string. Okay? Till this point, any doubt? Boys and girls. When we say that, we are saying some laws. Generally, we require some experimental verification for this. It should be experimentally verified. Otherwise, it won't be a law. It will become a hypothesis. There is an instrument called sonometer. I'll just show you that. Using sonometer, you can verify these laws. Now I'll show you the description about the sonometer. Actually, this is how a sonometer looks like. Remember, it is a hollow wooden box. Entire thing inside is a hollow wooden box. And you can see there is a metal stick like kind of arrangement here. It is solidly fixed to the box. There is a pulley here. And from here to here, you have a string that passes over And this is connected to weighing pad like this, pan. And some objects were dropped onto this. That creates some tension. Now, between these pegs, in between these pegs, I'll place a paper rider. Paper rider, and if you see, shape of the rider is like this. It's like a paper bent in the form of V shape, inverted V shape. Okay? Just by adding some loads, you can set tension in this. Remember, these bridges are sharp, that these points acts as nodes. Okay, sir, what you want to tell? How is this sonometer operated? How is this sonometer operated? Now you excite the tuning fork and place it over the box like this. Place it over the box. Now this tuning fork vibrations set forced oscillations in the string. And because of the forced oscillations, stationary waves might form here. Suppose if the tuning fork frequency and the natural frequency of the string matches, this portion will be in resonance with this tuning fork. When it is in resonance, maximum energy is transferred to the string. In such a case, amplitude is high. If the amplitude is high, what happens? String will flutter, of course. If it is high, what happens? The paper rider will slip from the string onto the board. It will slip from string onto the board. Got the point? This condition is called resonance. And at that point, the length of the string is called resonating length. Now, what you will do? Frequency of the tuning fork is same as frequency of the string, which is equal to 1 by 2L root T by mu. So, you are going to measure length as well as tension, means the load in the pan. So, how I will verify first law? See this. First law, what I am going to do is, I will fix the load in the pan. I will take 3 different tuning forks. 512 Hz, 480 Hz, 420 Hz. 3 such tuning forks. 511, I will excite and I will place this on the box. I will measure the corresponding resonating length. Similarly, 480, corresponding resonating length. Similarly, 420, corresponding resonating length. Now I got 3 frequencies and corresponding resonating lengths. If I can prove that F1 L1 is equal to F2 L2 is equal to F3 L3, what is that I am going to do is I am verifying the first law of transverse vibrations of stretched strings. Any doubt till this point? Boys and girls? Pakka. Have you understood? Now we will move on to the second law. See, if at all I wish to verify second law, what has to happen is I need to change tension or I need to change frequency according to the variation of the tension. But the problem is in market, whatever the tuning fork is not available. Here I am not taking any U-turn. For God's sake, just please remember, I am not taking any U-turn. What I am telling you is, in market, 512, 480, 420, maybe 360, maybe 380, maybe 340, something like that. These frequencies are available. Tuning fork with these frequencies are available. So you cannot change frequency of the tuning fork as you wish. For this purpose, I will do a small modification. Already I proved F into L constant. Now I will prove, instead of F into L constant, I will prove L proportional to root T. Actually, I should prove F proportional to root T. Rather, I am proving L proportional to root T. Means, now I will fix tuning fork. I will take only 512 Hz. Now I will take a 512 Hz tuning fork and I will exit here. I will post 100 grams weight in the span. That sets some tension. Accordingly, I will measure the balancing length, resonating length. Now what happens? I will maintain the same tuning fork and I will make the load as a 200 grams now instead of 100 grams. Next 300 grams, next 400 grams, next 500 grams, next 600 grams. For every 100 grams addition, I will measure the corresponding resonating length. Till this point, any doubt? So what I need to prove? Root T1 by L1 is equal to root T2 by L2 is equal to root 3 by L3 is equal to root T4 by L4 is a constant. Any doubt till this point? Are we clear? Okay. This is how I'll verify. Likewise, I'll prove root T by L is a constant. Vice principal, Ramesh. Right. Next. Second law is done. Third law. I'll take three different wives. Boys and girls. I'll take three different wires. Copper, gold, silver. Wrong. अरे नहीं मिलेगा market. Too cost. Brass, aluminum, steel wire. Right. Right. మీ క్లాస్ ఎన్నింటి దాకా 9:50 క్లాస్ అయిపోయింది అయితే I'll just close this after this. So what I am going to do is I fix those wires, aluminum, brass, whatever it is, three materials. Assume say I'm taking the same cross section, same frequency. So what I am going to do, I'll take brass wire, I'll fix the tension, say from 400 grams I will add in the pan. 512 at tuning fork will be excited. For brass wire, what is the resonating length? For steel wire, what is the resonating length? For aluminum wire, what is the resonating length? So three different wires, I'll measure resonating lengths. So I'll prove that L1 root mu1 is equal to L2 root mu2 is equal to L3 root mu3. If I have done, third law is verified. Okay, that's all. So